Hi there, class. Welcome to Lesson 8.2, Graphing More Complicated Rational Functions. So in our last lesson, we graphed simple rational functions, and so it seems to make sense that we're going to be moving on to more complicated rational functions. And remember, the ones that we looked at in the last lesson were in this form, where they were all different transformations of the parent function 1 over x, which is called the reciprocal function. And we talked about things like asymptotes, which were places where the graph was undefined, or they were these lines that the graph approached but never could quite get to. And so we're going to kind of expand on that and look at even more complicated rational functions. And our essential question is, what features of the graph of a rational function should you identify in order to sketch the graph, and how do you identify those features? So, in the last lesson we would identify the vertical and the horizontal asymptote from whatever the shift was, if there was any kind of shift, left or right, up or down, and then we would locate a key point by looking to see if there was any kind of reflection that would tell us which quadrants the two opposing branches would be in, and that key point, so we could kind of see whether there was a stretch or compression and how it close towards those asymptotes that bending point of the graph went. So we're going to start off by looking at some graphs of some more complicated rational functions. And in fact, the very first one, x plus 3 over x minus 1, we actually looked at some like that yesterday in the prior lesson. And if with that type, what we would have done is divided the numerator by the denominator, put it in that form where we could just look and see what the transformation was. And okay, so I did that, and this is what I got. And so I could see from this form that this was a slide 1 unit to the right, 1 unit up, and it was a vertical stretch by factor 4. And this is actually what the graph looks like on a picture on my graphing calculator. And you can see that that really kind of, agrees with what I just found out, that when I look at that, I can see that there is a vertical asymptote where the denominator is 0, which is at 1. And you can see if I go over here on my graph, I can see that there is a vertical asymptote right here at 1. I can see that this is slid up 1, so that's giving me a horizontal asymptote at positive 1, y equals, in other words, y equals 1, and the vertical asymptote at x equals 1. And then this is a vertical stretch, so you can kind of see that those curves are kind of pulled a little bit away from where those asymptotes intersect each other. So if I wanted to define the domain, probably the easiest way to do that is to use this set notation. And remember how that's written. We say x, and then this is read such that. And then basically in this case, you can see that this is really a continuous graph for every value except for when x is 1. And obviously we know why x cannot equal 1, and that's because that is where the denominator is made 0. And so again, what that really says there when I write the domain in that way is I'm saying x such that x cannot equal 1, and that's implying that it can be everything but 1. And that's where that vertical asymptote is. It's at x equals 1. So that's the excluded value from my domain, and that's where that vertical asymptote lies. So then I took a look at this next one. Now this next one looks much more complicated. I have two different factors on the top, x plus 5 and x minus 1, and on the bottom x plus 1. And again, if I kind of use that same logic to kind of guess where the asymptote, vertical asymptote, it's always really where the denominator would be made 0. That's the one value that x cannot have. Really, the numerator can be 0 as much as you want. That's no big deal, but the denominator can't be. So if I had to guess, I'd say x cannot equal negative 1, and let's real quick take a look at the graph. And that looks about right. I mean, when you look at where that vertical asymptote is, or where that break in the graph, and this definitely looks different. This looks like they took these graphs and stretched them quite a bit more, like so that they go up and down more. They're not just defined into two quadrants. So it appears that there's not any kind of horizontal asymptote here, but since we're just exploring vertical, you can clearly see that there's a vertical break there, and it seems to agree with what I speculated on, and that I thought it was at negative 1. So if I were going to give the domain, I would say that it looks like left or right there, there's only one break, and it's when x is -1, so x just cannot equal -1. Okay, and you can kind of see that these graphs are going to be changing. So now let's take a look at the next one. And again, if I had to kind of speculate on where the vertical asymptotes might be and the things that are not in my domain, if I look at that denominator, there really appears to be two different values that would make the graph undefined. I would see that it would be at -1 and +1. And that would mean there's two vertical asymptotes. So what would that look like? And that's actually what this graph is here. So you can see that right there, you can clearly see, I mean, it is kind of small in my picture, but you can see there that there are two vertical asymptotes because the graph is split up into three parts. And there's one like right about here and one right about here, which, sorry about that, hard to draw on that tiny little graph. But it definitely appears that there are two vertical asymptotes there, and they are right at those two values, 1 and -1. So if I had to, again, give my domain, I would say x such that x cannot equal 1, and x cannot equal -1 either. And so otherwise it seems like every other x value is really fair game here. So again, you can see as we add more complexity to the numerator and denominator, the more complex the graphs get. And then finally, let's look at this last one. So with this last one, it's a little harder to see what would make the denominator 0, and that's because it's in this expanded form. But if I took and factored that denominator, I could rewrite it as x minus 3 and x plus 2. So again, by factoring that denominator, I can see that if I was kind of, again, going on the same thought, that there's two places where this should break in the graph. It should have a break at when x is 3, and then when x is -2. So let me show you what that actually looks like. I'll pull up the picture. But actually, this is what it looks like. Now, that just looks like kind of one of those hyperbolas. It certainly looks like a hyperbola that was maybe reflected, but it looks like there's only one asymptote, and it actually looks like that asymptote might be at -2. I mean, I can see there's definitely a break there at -2, but then what's going on at 3? And that's the phenomenon that is called a hole in the graph, or a point of discontinuity. And so we're going to go ahead and now take a look at the table that goes along with this graph, and you're going to see that, in fact, the two places we just discussed, 3 and -2, they're undefined there. In the table, they say error. That's how you'll see like an undefined spot in the graph for the output. But at the same time, we don't see an asymptote here on the graph. And looking right here at this table, you can see right here at -2 and at 3, it says error, which means that's the graph does not exist there. And so we were right in saying that maybe there was an asymptote at -2, but what's going on at 3 is actually a hole. But that is still an excluded value. When I think about the domain, I know I have to say that x cannot equal 3, and also that x cannot equal -2. But in fact, there's a hole there. So we're just going to say there's a hole, and we'll talk a little bit more about that in just a second, at x equals 3. And then rather than looking at this next function, this x plus 1 over x squared plus 3x minus 4, we're going to go ahead and turn the page and kind of summarize these findings about vertical asymptotes and holes. So as you've seen, there can be breaks in the graph of a rational function. These breaks are called discontinuities. So asymptotes are discontinuities, but there are really two different kinds of discontinuities. There are these infinite discontinuities, which when a rational function has a factor in the denominator that is not also in the numerator, an infinite discontinuity occurs at the value of x for which the factor equals 0. On the graph of the function, an infinite discontinuity appears as a vertical asymptote. So that was what was going on when x was -2. There was that vertical asymptote. That was an infinite discontinuity. But when a rational function has a factor in the denominator that is also in the numerator, a point of continuity occurs at that value for x, which the factor equals 0. So in other words, the value that would make that factor 0, that actually creates a hole in the graph instead. So now it's not really apparent on a graphing calculator. You can't really see that hole, but when we looked at that table, we could clearly see that that was an undefined spot. So it's almost like, not as much of a barrier. The graph just kind of approaches that spot, jumps right over it, and then continues on, whereas with an asymptote, it kind of like butts up next to it, kind of gets closer and closer and closer to it, eventually gives up and jumps on the other side to continue the graph. So that's how you can find if, excuse me, if you have a common factor in the numerator that's also in the denominator, that'll create a hole. So let's go back and look at that other example. So this problem right there is the same one that I have right here. And if I were to take 2x squared minus 3x minus 9 and do the AC factoring on it, this is how it turns out. And you can see here that there is a common factor in the factorization of the numerator, that x minus 3, and in the denominator. And so essentially what happens is those two cancel each other out, but there is still some net effect on the graph, and that effect is to create a hole, and that hole is at the value of x that makes that binomial equal to 0, which is at 3. So let's go ahead and take a look at that one example. X plus 1 over x squared plus 3x minus 4. Let's go ahead and factor the denominator so we can kind of see where we might have some issues with the domain. And I can tell that when I factor that, I'd get an x plus 4 and an x minus 1. And in fact, in this one, I don't see a hole. There actually is not a hole. It's close. I mean, the factor in the denominator is x minus 1, but the numerator is x plus 1. So there is no hole here, and there's just two vertical asymptotes. And if you type that in your calculator, also, although you have to be really careful when you are putting these more complicated functions in your calculator, you'd have to make sure you go back to the original, put the entire thing in parentheses, okay, like the whole numerator and the whole denominator, to separate so that the calculator knows what's actually in the numerator and what's in the denominator. But if you graph that, you'd actually see there are two asymptotes, one at -4 and one at +1. And so x cannot equal -4, and also x cannot equal 1. That's actually where the asymptotes would lie. And you can confirm that by graphing and looking in the table.